Okay, so this is workshop 8, where one of the things we're going to do is have a proper look at characteristic functions of sets and various ways of counting things, and maybe we'll even prove the inclusion-exclusion principle. Let's see. But first, I'll give you a chance to use what I just told you, which is the binomial theorem, to help you find the coefficient of x squared in 2 plus x to the power 10. And so the end of the last lecture should be quite relevant to you here. Well, near the end anyway. And give you a couple of minutes to try and work this one out and see what you get. Oh, I need to zero the votes. Hold on a second. Haven't zeroed the votes yet. Okay, I've deleted the votes, so you can vote whenever you like on what the coefficient of x squared in 2 plus x to the power 10 is. And we'll just come around and see if people can remember how to use the binomial theorem. Oh, and I'll pause the recording. First of all, let's see what you went for. So we had 30 answers with a big majority going for C, and the majority got it right again. Let's see where that came from. Okay, so I think I'll use the x plus 2 to the power 10 and the binomial formula we had earlier. So x plus 2 to the power 10 is equal to the sum from k equals 0 up to 10 of 10 choose k times x to the k times 2 to the 10 minus k. Now, we're interested in how many x squareds there are, which means we want to know what happens when k is 2. K equals 2, the coefficient of x squared is 10 choose 2 from that bit, and from the other bit we get a 2 to the 8. But we have to work that out. 10 choose 2 is 10 times 9 over 2. Then you multiply that by 2 to the 8, and you get 90 times 2 to the 7. Any questions about that calculation? The one thing you should get used to is to know how to find 10 choose 2. But I showed you some quick ways of working these things out at the end of the last lecture. So 10 times 9 over 2 is the quickest way, I think. So 10 choose 2 is actually 45, but you throw one of the 2's from the 2 to the 8 into it to get you your 90. Okay, so let's have a look at the next question. But before we do that, I want to remind you about sets and their characteristic functions. I say here a function from x to the 2 set 0, 1, called the characteristic function. Actually, quite often we regard this as an integer valued function as well. So this is one of those cases where I'm not quite as strict on the codomain as usual. Okay. So for the moment we'll say that it takes values that are either 0 or 1. So you could regard it as a function taking value in this set, or you could regard it as a function that takes values in the integers, but it only happens to use the values 0 and 1. And it counts 0 if you're outside the set, it's 1 if you're in the set. And there are various different notations for it. So this is the Greek letter chi, which I shall attempt to draw myself. But you should bear in mind, this is the Greek letter chi. Chi sub e means a characteristic function of e. Probability, you might see it as 1 sub e or various other kinds of symbol similar to that. And if you sketch it on the number line for an interval, if e is the closed interval 0, 1, y equals chi e of x looks like the following. So because I made it closed, it includes these points here, and then it jumps down and carries on along the axis there, and oh, I see, it jumps along here as well, which happens to be at the origin, which is a little awkward. But there you go. That's y equals chi e of x when e is the unit interval from 0 up to 1. It's 1 if you're in the set, and it's 0 if you're outside the set. Now what do you do with that? You can use characteristic functions to count the number of elements. Now, I'll just stick to finite sets here to avoid any technicalities. To make sense that what you can do is you can look at all the elements of x one at a time, and you work your way through all the elements of x, and for each element that's in E, you count 1, and for each element that's not in E, you count 0. That will give you the number of elements in E, because for the ones that are in E, you get 1. And the ones that are not in E, you get 0. So you'll get exactly the number of elements of E. And that's how this works. So you can count the number of elements in E just by summing over x in x, these characteristic function of E of x. And that can be useful, because we're going to see some useful relationships between characteristic functions for sets when you do unions, intersections, and things like that. And then that will help us to get at this inclusion-exclusion principle. So any questions about why it is that if you add up over all the different elements of x, the characteristic function of E evaluated x, you get the number of elements in E? Does that make sense? You count 1 for everything in E, and you count 0 for everything outside in E. So you get 1 for every element of E, which is the number of elements in E. But if you're not sure about it, try a few examples. Okay. Now, I won't get you to vote on this. Last year we would have voted with coloured card, but this year I'll just get you to work it out, and I'll give you some comments either. So you've got some universal set X, which, if you want, you can think of as a finite set. We're mostly interested in finite sets, but you don't have to, and this result doesn't require any of the sets to be finite. So complements will mean complements in X. So a complement here means X take away A. But X is our universal set, and that's what our characteristic function is defined on. And 1 is the constant function 1. It takes 1 at every element, so that might be useful. And there are 3 different things I want you to look at. I want you to look at the set A complement, A intersection B, A union B, and try and work out for each of those 3 which of these functions gives you the characteristic function. And so, for example, this one would be this chi A plus chi B. That means it's the function that takes x to chi A of x plus chi B of x. And chi A times chi B, that's the map that takes x to chi A of x times chi B of x. And so I want you to think about the characteristic functions of A complements, A intersection B, A union B, and try and figure out which one is which. But there's 4 things on offer here, so they can't all be right, perhaps by the pigeonhole principle. Okay. So we'll come around and see if you've figured out what this means. But there's no voting this time. Okay, I've started the recording again. Let me give you some ideas of how what's going on here. I won't go through them in full detail, perhaps. But still, okay. So the characteristic function of A will mean that you're supposed to be 1 for the x's that are in A, and 0 for the x's that are outside A. Whereas for A complement, you have to swap it round. You want to have 1 if you're outside A, and 0 if you're inside A, which means you should do 1 minus the characteristic function of A, and that will give you the characteristic function of A complement. Characteristic function of A times the characteristic function of B. Well, the characteristic function of A is 0 if you're outside A and 1 if you're inside A. And the characteristic function of B is 0 if you're outside B and 1 if you're inside B. If you're in both, you get 1. But if you're outside either of them, you get 0. And that's exactly what you want for the intersection. Okay? So if you're in the intersection, then you have to be in A and B, which is exactly the same as having both chi A and chi B being 1. And so you pick up that the characteristic function of A times the characteristic function of B is the characteristic function of the intersection. You can do all these things by case analysis. If you're ever unsure, you could just check that it works in the 4 different regions. And if it works in the 4 different regions of the Venn diagram, you're okay. Now, the first one looks like it might be the characteristic function of A union B, because somehow you're going to get 1 for lots of things in A and 1 for lots of things in B. But there's a problem on the intersection stage, because if you took an x that was in the intersection, if there is one, then chi A and chi B would count you 1 each, and you'd get 2, which is not a value a characteristic function should take. So something goes wrong on the intersection because everything gets double counted. So chi A plus chi B is almost right for the union, but you get 2 on the intersection, so you better subtract off chi A, chi B, or the characteristic function of the intersection. So 3 is the characteristic function of the union. And chi A plus chi B isn't any of them, though, as we'll see in another workshop, that it's equivalent to the characteristic function of the symmetric difference if you work modulo 2. Anyway, we won't worry about that today. Any questions about those 3 characteristic functions? So now we move on to the abstract version where you've got n sets. And I mentioned that you may want to use De Morgan's laws here. Product of characteristic functions, this is the product notation, remember, so that means characteristic function of A1 times the characteristic function of A2 times the characteristic function and so on times the characteristic function of AN. This is the same where you multiply the 1 minuses. And it says De Morgan's laws might be helpful, so the kind of thing you might find useful, I'll use B's instead of A's, and I'll use K's instead of J's, but it doesn't really matter. The union from K equals 1 up to n of BK complement is equal. The complement of the union is the intersection of the complements. And the complement of the intersection the complement of the intersection is the union of the complements. You can use those freely. Those are standard De Morgan rules for relating the unions and intersections of sets and their complements. Okay? So let's see how we get on with these. It's very similar to the last one, but more abstract. Okay? So I'll pause the recording there and see if people have got any ideas on this one. Right, okay, and the second one, where you multiply the characteristic functions together, that's the characteristic function of the intersection. So, okay, I don't think I've got room to do the whole thing. The characteristic function of the union turns out to be the fourth one. Let's try and figure out why that is. This 1 minus chi aj, that is the characteristic function of aj complement. When you take take away a characteristic function is a characteristic function of the complement. So if you multiply the characteristic functions of the complements, you'll get the characteristic function of the intersection of the complements. So this is the characteristic function of the intersection from j equals 1 up to n of aj complement, which is almost what you want, except the union is the complement of the intersection of the complements. So you have to take it away from 1 again. That's equal to the characteristic function, that's because you see the union from j equals 1 to n of aj is equal to the complement of its complement. You can complement it twice. That'll get back to where you started. That's equal to, De Morgan's laws will say this is the complement of the union is the intersection of the complements. So leaving that in brackets and it's still going to be complemented. I use De Morgan's laws to get the thing inside there is the intersection from j equals 1 to n of aj complemented. And so the characteristic function, well, you know the characteristic function of this is to multiply various things together, and the characteristic function of its complement is to take that away from 1. The characteristic function of this set is 1 minus the characteristic function of this set, and this we can work out as 1 minus, that's a product, j equals 1 to n, of, then you need the characteristic function of aj complement, which is 1 minus the characteristic function of aj. Now, you can actually start to multiply this out in a few cases, like if n equals 2, this gives 1 minus chi A1, 1 minus chi A2, which is equal to, you can just multiply it out and work it out, chi A1 plus chi A2 minus chi A1 chi A2, which you could also write as chi A1 plus chi A2, take away the characteristic function of the intersection. And if you've got 3 of them, you get, when you work it all out, chi A1 plus chi A2 plus chi A3 minus chi A1 intersection A2 minus chi A1 intersection A3 minus chi A2 intersection A3 and plus chi of the intersection of all 3. That last one is obtained by multiplying. You see what you get for the brackets. You're subtracting. So what's the coefficient of chi A1 times chi A2 times chi A3? Well, there's 3 minus signs in there and another minus sign outside, so it comes out positive. That's why you get plus chi A1, chi A2, chi A3, which is this one here. The chi A1 intersection A2, that's chi A1 times chi A2. You get that from these multiplying the minus chi A1 by the minus chi A2, but then that's 2 minus signs gets it plus, but then you subtract it, so it's minus, and that's why that one comes out minus. Oh, and something's missing. That should be chi A3. So I'm going to leave it to you for the rest of the time. We'll come round and talk to you about this, but I'm not going to do this in full anyway. But I've pretty much given you a hint now as to how to do the 2 set 1 and the 3 set 1. And the problem with the more general one is the notation for it. But I don't think we're going to have time to do that in detail. So let's give you a few minutes to see if you can figure out how to use what I just wrote, along with, the thing we had at the very beginning, the fact that if you want to see how big a set is, you add over all the elements in X the characteristic function, which is something we had earlier on. If you take these inequalities and sum it over X in X, so if you take these equalities of characteristic functions we had and sum over all X in X, you'll start to pick up the inclusion-exclusion principle. Okay, but let's see if anybody's made any progress on trying to find some decent notation for this. I'll pause the capture and we'll come round and have a chat.
So then we're assuming that then you say that no section
Okay, so before you leave, don't forget, if you haven't handed in your coursework, there are these 4 trays to hand your coursework into. But I guess we're out of time today, so I'll stop the recording there.